just to recap, we have converging mirror, which for converging for mirrors, that means it's a concave mirror. We have an optical axis, an imaginary line that passes through the center of the mirror. This would be the radius of the sphere that makes the mirror. From here to here would be the radius. This is the center of curvature. Half of this distance here is the focal length. So that should be the focal point right here. We're going to deal with 3 rays. First one is called the parallel ray. And the parallel ray comes in parallel to the optical axis and goes out, I'm going to put quotations around it, through the focal point. Now when I say through, in quotation marks, it's because in other drawings in a little bit, it's going to be a little weird. We're not going to be able to actually go through it, but we still involve it. So I'll use the word quotations for now. So the way that's going to look is this. Parallel to the optical axis means it's leaving this point and going right along. That's why we like graph paper for this. Parallel to, well, the optical axis. So we're going to come in this way. And hit the mirror. I'll do it in red. Doesn't matter what color I do it. You don't even have to do it in. Let's see if I can zoom in on this a little bit. You don't even have to do it in color. So, after coming in parallel, it hits the mirror and goes through the optical axis. Through the focal point. So it's going to go from that reflection right through this point. I tend to work in pencil first in case I make a mistake, and then I'll put the colors on it later. Goes off this way. Extend your lines all the way out as far as you can on the paper that you're working with, because at this point we don't really know where the image is going to be, so we have to account for all possibilities here. Now, just a little bit of background. There are an infinite number of rays that leave the tip of this object. So this could be the top of a person's head or their nose or something. It doesn't really matter. But this is just a representative piece of this object. And there's an infinite number of rays. Light hits it and they go off in every direction. Well, you don't need to draw every ray that leaves and hits the mirror. What we draw are 3 of them that we can use a little geometry to figure out where they go, and then they represent what happens. Because what the truth is wherever we end up with our image, which is going to be down here, I believe, every ray that leaves here and hits the mirror will end up at that spot. Not just the 3 that we're doing, but all of them will if they hit the mirror. We just need some to give us a feel for where that's going to be. So the first one, like I said, is the parallel ray. The second one is the chief or center ray. I learned it as the chief ray. I still use chief ray. It comes in through the center. I will once again put quotations around the word through. We'll just, in the next diagram or 2, we'll see why. And then, quite simply, goes right back where it came from. And the reason for this is when a ray, any line in geometry that goes here, a couple geometry facts that if you don't know, you should probably know as you go through life. So if you have a circle, forgive my circle if it's ugly, but some things that are true. A radius, a line that leaves the center and goes to the circle, will always hit the circle so that it is perpendicular to whatever tangent line hits that point. So for example, any radius I draw, wherever it hits, let me move this up so you can see it, wherever it hits, it will be guaranteed to be perpendicular to the tangent line at that point. So this comes in right along, optically, right along the normal, and will therefore go right back where it came from. The angle of incidence is 0, the angle of reflection will be 0. So, for that reason, this chief ray or center ray is pretty simple to draw. We saved the most difficult one for last, that way we can cheat. I'll show you. So it leaves the tip of the object, goes through the center, hits, and goes right back where it came from. I'm screencasting and I can't pause. Oh, my chair's I think I usually do that one in green, if I remember correctly. So, chief ray comes in, hits, goes right back where it came from. Now, at this point, we actually can tell where our image is going to be already. The last ray we do is just to back us up. I know the image is wherever those two meet. So I know that my image is going to should be right here, if I've done everything right so far. I dot it, and since the rays left the tip of the arrow, where they meet is the tip of the arrow. Common mistake is people get here and they draw this. But that's not right because these rays left the tip of the arrow, not the base. So this is an indicator, if we remember that the base of the arrow is always on that optical axis, that this image is being inverted. Now, we always do a third ray to back in an official ray diagram, we do a third ray to back ourselves up. Now I'm now going to teach you how to make sure that things come out nicely. Because I don't know about you, I'm pretty confident that what I did so far is right. And this is just a sketch. If you draw them to scale, they can really help you if you're doing the math to see if your math is about right. So in order to do this, let's go through what the last ray, which is a focal ray, does. It goes in, it's just the reverse of the parallel ray. It goes in, quote, through the focus, or the focal point, and goes out parallel. Well, let's start from the end. So that means that when this ray comes off the mirror, out here somewhere, it's going to come parallel to the optical axis, correct? So we need it to come out like this, and if in a world where we do this right, we want it to go through that point right there. Otherwise, they don't all meet there. So then you ask yourself, all right, well, if that's the case, I see where these two meet right here. If I go parallel over, where would it need to hit the mirror? It would need to hit the mirror right about there, wouldn't it? Remember, I'm cheating now. This is me trying to make sure everything comes out nicely. So I keep this spot in mind. In a perfect world, we'd put our ruler down, and light would leave the object, go through the focal point, and hit right there. If it doesn't quite hit right there, I take a little bit of license and go a little bit above or a little bit below the focal point to make it work. So, for example, here, if I line this up with the focal point, and I try to get those 3 points. So I have this one here, my focal point here, and the tip of the object. I'd really like to get those to line up pretty closely. So that's not bad. I think I could do that. It's close enough. And so the ray leaves, goes, quote, through the focal point, and hits right there. Do this one in blue. So it comes in like this. Hits and goes out parallel to the optical axis. And I'm no dummy, I know where I need it to go through. It's right through that point there. And if you use nice thick lines, you can generally make it look really good. I didn't put the red on this exiting right here. So, what would be your image characteristics? Well, let's go with real or virtual. If you've had a chance to do some of the other drawings, you may have come across a virtual image. You know a virtual image when you have to start dotting back behind the mirror. We did not have to do that. None of our lines are dotted. We never worked back here at all in the virtual world behind the mirror. So this is a real image. Another indicator that it's real is that it's inverted, right? The two tend to go together. So this is a image characteristics would be a real, inverted, and I think smaller, right? Reduced image. And you know what? I'm going to do something I haven't done on one of these before. Let's do this. Let's combine what we just did with the following. So here we go. If this is a spherical mirror, I'm going to say that its focal length is, let's say this drawing is perfectly to scale. Its focal length is 5.7 centimeters. So its focal length is 5.7 centimeters. Positive. Why is it positive? Because it's a converging mirror. If it was a diverging mirror, they would look like this, by the way. This would be an example of a diverging mirror. All right, with the focal length behind the mirrored surface. If it was diverging, it would be a negative focal length, but for here, it's going to be positive. So we're going to do a sample problem to see if this all makes sense. What would be our object distance? Your object distance is the distance along the axis from your object to the mirror, the center of the mirror. So in our case, call it 18.2. So the object distance is 18.2 centimeters. This is one of the only situations in physics where working in centimeters is okay. We just keep everything in centimeters. Unless you're dealing with telescopes, you're probably not dealing with reflective mirrors that are in the order of meters in their focal length. So generally, we work in centimeters, and if we work across the board in centimeters, there's no reason to switch into meters. So that's kind of nice. What would the image distance be? Now, we could measure it here, and that's what we're going to do eventually to see how close we get. But mathematically, this is what we would do. Oh, and by the way, let's figure this out too. Our height of our object is about 3.3. So for the record, the height of the object is about 3.3 centimeters. Okay. So we're just doing this to compare how the math and the drawing can kind of be used together to see if you're doing something right. So let's find the image distance. Well, we know that 1 over the focal length is equal to 1 over the object distance plus 1 over the image distance. And I got 1 over 5.7 equals 1 over 18.2 plus 1 over the image distance. And so the 1 over that image distance is going to be 1 over 5.7 minus the 1 over 18.2. This is where I would break out my calculator and figure out. Now I use the inverse key. And I probably won't be able to see that on the video, but so 1 over 5.7 minus 1 over 18.2, and then you'll have this 1 over image distance is equal to 0.1205. Do not forget to flip it right side up again, because this number 0.1205 is equal to 1 over the image distance. So you need to, the key will look like either this, or you can just do 1 divided by 0.1205, I mean. All of those, there we go. All of these will do the job, but we have to flip that right side up again. So boom, and I get 8.29, or 8.3 we'll call it. So I get an image distance of about 8.3 centimeters. Okay, so how good are we? 8.3 centimeters. Oh, look at that. If you can tell, that's about 8.3 centimeters in that neighborhood. Okay. So if you draw it to scale, it should work. And I'm not saying I would just do the drawing. If a question asked me to figure out something exactly, I would do the math. But I would, at this point, having done the drawing and the math, and having them come that close, I'd be like, there's no way in heck I'm getting this wrong. Right? I know this has to be right. How tall will we expect the image? So let's figure out the magnification. Magnification is the ratio, one way to find it, is the ratio of the image distance divided by the object distance. We use the opposite because the magnification is going to tell us if it should be inverted or not. So I use the opposite of 8.3 divided by 18.2. Get a magnification of negative 0.456. So about 45%, 46% of the original. So this thing here should be about half estimate of this. I can find out exactly how big it's going to be if I keep in mind that magnification is also the height of the image divided by the height of the object, which means that the negative 0.456 is also equal to height of the image, which I don't know, divided by the height of the object, which was 3.3. And that gives me an image height of negative 1.5. What's the significance of the negative? Our image is inverted. That's why that negative is there. And it claims that it should be about 1.5 centimeters. And look at us, we are awesome. That really is what it comes down to. You were awesome, by the way, if you're watching this before we did this. But you're even awesomer now. All right, next one we'll do in the next video will be one of the other ones, something we haven't done yet.